So today my topic is Bayes learning via stochastic gradient Langevin dynamics. Our goal for this paper is to sample the distribution of Bayes posterior for model parameters given data using Langevin dynamics. Usually such algorithm requires computation over a whole dataset and is very inefficient when the dataset is very large. So we may want to use the idea of stochastic optimization. Here's the equation for the algorithm, and we see that the epsilon t here is the sequence of step sizes that satisfies such properties. Also, when t goes to 0, the step size will converge to 0. Here's the equation for Langevin dynamics. dWt represents a Brownian motion that introduces random fluctuation. With fixed step size epsilon, we can take the update in equation 3. Then we combine the idea of stochastic optimization and Langevin dynamics. It gives the equation 4. This is the method for this paper. Then we have the question. When t gets large and epsilon t goes to 0, will the parameters sample t approach to the true posterior? We note that we have two random terms, one from injected Gaussian and one from stochastic optimization. The answer to the question is yes, because for each fixed step size epsilon 0, we have a subsequence theta t with step size approaching to epsilon 0, and the total injected noise will dominate the noise from stochastic optimization. That is to say, the subsequence mimics the original Langevin dynamics with fixed step size epsilon 0. And so the new proposed algorithm will converge to the true posterior. However, this method suffers from the problem of unknown amount of noise brought by stochastic optimization. So this method only works when step size is small or when a good estimate of the noise is available. We may want to propose a method that self-adapts to the unknown noise with the help of some additional variables. That is my hypothesis. So here is the stochastic Langevin dynamics. Theta here is the parameter, p is the momentum. I know that it may look different from the original algorithm, but they are the same. And then it's a key part of the paper. In statistics, physics, a canonical ensemble represents the possible states of a system in thermal equilibrium with a heat bath at a fixed temperature T. So for the distribution, it will satisfy the thermal equilibrium condition. It's the equation in 4. And in Bayes stats, in the dimension of the theta and kbt is 1. Also, it's noticeable that Langevin dynamics will also satisfy the thermal equilibrium condition, while the stochastic Langevin dynamics does not have to do so because of the unknown noise from the stochastic optimization. That is to say, the dynamics may drift away from the thermal equilibrium if the variance of the stochastic optimization is poorly estimated. So we may want to incorporate the thermal equilibrium condition into our model. To do that, we introduce the additional variable psi. When kinetic energy is larger than 1/2, the psi gets bigger and P will experience more friction. Well, here is our new algorithm. And if the mean kinetic energy is lower, the psi gets smaller and P experiences less friction. This is how to self-adapt to the unknown noise with the additional variable based on the thermal equilibrium condition. And here it gives the mathematical justification. In the first part, it tells us when the algorithm will converge to the true posterior. It gives us general recipe. And the second part verifies that our new algorithm satisfies the general recipe, so it will converge to the true posterior. Then it's the result of the experiment. You can see that our new algorithm performed very well, while our old algorithm will converge only when the step size is small and the injected Gaussian is big. So this is our paper, and in the future, I expect I can incorporate more stochastic optimization into this model.